Hey you guys, this is Mr. Sal. I'm going to be out, so you guys should start on this bell work. And please be nice to the sub if you misbehave in any way, or I find out that you misbehaved. The sub is going to take your name down, and you will pay. All right. Probably send an email home to your parents, letting them know what you have done and how disrespectful you've been. So please don't do it. Be nice to the sub. They're doing their best they can, and they're doing me huge favors. So in the meantime, while you're behaving, go ahead and get started on the bell work throughout this video. I'll be pausing so that you guys can look at stuff and read it, but since you'll be doing this on your phones as well, you may pause the video or even speed through it for some of the parts. Okay, so let's take a look at these and then get them done. I'll have the corrections to the homework as well. So take a moment, start on the bell work, and then we'll get to the homework. All right, there are the answers to the bell work. And here are your homework answers. So go ahead and mark anything wrong that you got. In 1C there, each of the pairs is worth 1 point. So if you missed one of those, just 1 point off. And you're supposed to label the X and Y's as well. Then the graph there, 1C, that should be worth 5 points. So go ahead and take your score down. We'll take scores when I get back. So keep that in mind. You're going to want you to write your score down. We will not be correcting this in class next time. So take your time. Again, if you need to pause the video, then do it. But I'm going to give you some time anyways. All right. So now that you have that, we'll go ahead and take a moment and get started on the classwork. If you haven't gotten it yet, please remind the sub that they need to hand that out now. And I'll give you a few seconds to get that done too. Sketch the general appearance of the graph of the equation y equals mx plus b. So if we look at this thing, here are some x's, and we can just make any kind of line that we want. So if this was our line right here, that looks pretty good. We have our y-intercept here. That's the b value, 0b. And then good old sloppage is determined by rise and run. Then what do m and b represent? M is the slope and b is the y-intercept. Then what makes this graph linear? The slope is a constant rate of change. Now we should have already known that, so you may want to take a moment and write those down. Alright, complete the table of values for the functions shown in the table below. Using the table of values, predict what the graphs of the equations will look like. Compare the tables to the table for y equals x. So, where y equals x, we just take the x value, and y is the same thing. So they've got a negative 2 there, negative 1, 0, 1, and 2. Now again, it's important for us to remember and think about what the graph would look like on this thing. So if we had these values with 1 and 2 and negative 1 and negative 2, then we'd have 1 and 2, negative 1, negative 2, and where y equals x, we would have these points, something like this, which then gives us, that's in the origin by the way, should give us some kind of straight line like this, and it's diagonal. So what about y equals the absolute value of x? Well, we're going to take the absolute value of all these x's, so the absolute value of negative 2 is 2, the absolute value of negative 1 is 1. The absolute value of 0 is 0. Now again, the absolute value is how far away that value is from 0. So 1 is 1 away from 0, and 2 is also 2 away from 0. And now we got this x squared stuff. So x squared may be important to remember that we're just taking the x and multiplying it by itself, which is x squared. So negative 2 times negative 2 is positive 4. Negative 1 times negative 1 is positive 1. 0 times 0 is 0. 1 times 1 is 1. And 2 times 2 is also positive 4. So notice these values kind of came down there. 4, 1, 0. And then we went to the same values, 1 and 4. Alright, so what about 1 over x? So x is negative 2, this first one. So that would give us 1 over negative 2. 1 over negative 1. That can be simplified to just be negative 1. Now here's the thing, though, is 1 over 0, that's undefined. So we don't actually have a value for that. Technically it's infinity, right? Because 0 can go into 1 in infinite number of times. Then we got 1 divided by 1, which is 1, and 1 divided by 2, which is 1/2. I'll just keep those as fractions. And then we got the square root of x. You just want to use your calculator for these. And these are the values you should get after plugging that into your calculator. Now this right here is 2 to the power of x. And you may have to use your calculator for some of these, but 2 to the power of 0 is 1. We haven't really gone over exponential powers, if I remember right, so that may be something you just have to use a calculator for. 2 to the power of 1 is 2. 2 to the power of 2 is 2 times 2, which is 4. 2 to the power of 3 is 2 times 2 times 2, which is 8. And then another 2 would give us 16 there. And again, you could have used your calculator to find these values too. All right, so we got x plus y equals 6. So x again is negative 2 for this first one. Negative 2 plus what is 6? Well, that would be 8. Now, it may be helpful to write this as an equation, right? So this next one would be negative 1 plus y equals 6. And then how would we solve that? Well, we'd have to add 1 to both sides. And that would tell us that y is 7. So when x is negative 1, y is 7. So when x is 0, y is just 6. When x is 1, 1 plus what is 6? Well, that's 5. 2 plus what is 6? 4. And you may have noticed the pattern as well. These are just decreasing by 1 every time. That is because of the sloppage. Now this one's unique, but we did see this on the nuggetizer stuff, right? When y is 6, well, this is telling us the equation y equals 6. So when x is negative 2, y is 6. When we put in negative 1 into that nuggetizer machine, what comes out? 6. And it's the same for all of these, okay? And that's because y is just 6. All right, so looking at all of these ones that we have, we need to identify which of these go with the graphs. Now, we did include the tables with these, but we're really just looking at the functions here at the top. So, this first one, we can see that the values come down, and that's at a constant rate. It hits 0, the origin, and then it comes back up, right? Now this is at a constant rate, so it can't be x squared right here. Another one, I mean, we could look at some that go through 0, 0. This one doesn't indicate anything about when x is negative. And now this first one right here indicates that it should come down like this. But that's not what's happening on that line, so it's not this one. Another one that goes through the origin. The only other one is this absolute value of x, which does show that, right? When x is negative 2, right here, then y is 2, and then it comes down, and then it goes back up. So it looks like this one is y equals absolute value of x. Now this next one we did do already, and it's kind of indicated on that absolute value of x stuff. This one actually is y equals x. And what about this one? This is just a straight line. Now again, we don't have any values on this thing, but we should be able to determine it with just the table. So it's just a constant value of y, right? I mean, y here is the same value y here. No matter what the x is, well, that would be y equals 6. All right, you take a moment and try these ones out. See if you can figure out which is which. Of course, we did use this one already, this one, and this one. So you only have about 5 choices to choose from there. All right, so here are the answers, and let's see why. Well, this first one here, notice these lines are getting really close to the y-axis here, and it's going downward as well. Now, we didn't really see much of this stuff right here, but we did see some of this stuff on, where am I looking? Oh, there's 1 over x right here. The only value that shows where the y-axis, where x is 0, so x is 0, that doesn't really have a value is this undefined stuff. So we have y equals 1 over x right there. Now y, this one is kind of like the one that we had with the absolute value stuff, but the absolute value looks like this because it's a constant rate of change, which makes this a straight line here and then straight this way. Now overall it's not a straight line because it did break the pattern, but this one is increasing rapidly as we go to the right, because this is just going to keep going higher, and the one that indicates that is x squared, right? Like if we had 3 here, that'd be 3 squared, which is 9. 4 is 16. By the time you get to 10, you're going to be at 100 there. So it's increasing very rapidly. Not only is it increasing rapidly to the left, but also to the right, but also the left. Because as we make this more and more negative, the y values are going to become increasingly more positive. Now x plus y equals 6. We can look at the values on that table right there. Right, when x was 0, we had something like 6. When x was -1, we had 7, -2, 8, right? And then maybe when x was 1, it just kept going down here until finally you may hit 0, where y is 0. The x, of course, would be 6, which would have been a little ways down this table. But it definitely reflects the values that we have in the table. Alright, then there's only 2 more. So starting off with this one here on the left, and yes, we have already used several of these, right? And the only 2 that remain are y equals the square root of x and y equals 2 to the power of x. Well, notice both of these start at 0, where y is 0, and then it shows us other values. So when y is 1, maybe we get the 1. When y is 2, it's not increasing very fast right there, right? For the square root of x, so this one has to be the square root of x right here. Y equals the square root of x. And this one shows a very rapid increase. 0, 1, 1, 2, 2, 4, 3, and then it just keeps going up right there. Okay? So this one has to be y equals 2 to the power of x. So that was 3, 8 right there, right? Yeah, that's good. Alright, number 4, consider the area of a square as a function of the side length of the square. Draw pictures to represent these squares. The first 2 have been drawn for you, so we'll have to draw a little bit on this one. So starting off, we see that a side length of 1 produces an area of 1, and a side length of 2 produces an area of 4. So if we had something a little bit bigger like this, and split it up like this one, well, then we see a side length of 3 has an area of 9 squares. And then, of course, we'll just increase the size of these things so that hopefully it kind of reflects what we have. 3, 4, and so a side length of 4, we can count those squares. There would be 16. So what do you think the area of a side length of 5 would be? Yeah, we should get 25 out of that. So there we go. There's the table, and we did draw a couple of those pictures. I just don't have room for 5. So I've gone ahead and put these on a graph for you just so you can kind of see what it would look like on a graph. And we've seen this already, right? We did do one of these like this. So what is the dependent variable? Well, it appears right here that the area is depending on the side length of the square. So the side length is independent and the area is dependent. So we'll just label those. Side length is independent, area is dependent. All right, but let's go ahead and write an equation to model A as a function of S. And we can see that the area, if we wanted to find it, would be the side length. And what are we doing with the side length? We're just multiplying it by itself, so we're going to square it. We will not write that out as side times the side because it would, well, it would kind of spell some bad words there. So we're just going to write it as S squared. So does this pass through the point 864? Well, we're going to have to use the equation that we made for that. A equals S squared. And right there, the side length shows us is 8. And what is 8 squared? May need a calculator for that, but you could use the multiplication charts in the back of the classroom. It does equal 64, so the answer is yes. How do we know? Because we used the equation on that. Well, what does that represent? Well, that means we would have a square with a side length of 8 and an area of 64 square units, whatever the units are. So there's 3 more ordered pairs that this graph passes through. So we did have the 864, so we're not going to include that one, but we could use 636. 6 times 6 is 36. 7 times 7 is 49. Maybe if you wanted another one, 10. 10 times 10 is 100. That's a pretty easy one to use. Is this function linear? We can tell from the graph that there's some curvature here, right? It's definitely not a constant rate of change. And so as this thing continues to go to the right, it's going to get much bigger and much bigger. So this one is not linear, and we can tell that from the table there. I'm sorry, from the graph. The table shows different rates of change. For example, from side length 1 to 2, we increase the side length by 1. The area increased by 3. For it to be linear, it would have to be a consistent rate here. But the area here increased by 5, while the side length only increased by 1. That is why this is not linear on the table. For the equation, right, we had A equals S squared. It's not with the equation because of the square. Now, if that square was with a number, it wouldn't be a big deal, but this is with a variable which is changing, so that is why the equation is not linear. All right, well, what about the perimeter of a square as a function of the side length of the square? So perimeter, and this is a square, so it's just 4 of the same side lengths. We can just add it to itself 4 times. 1 plus 1 plus 1 plus 1 would give us a perimeter of 4. Same with 2. But notice if we're adding the same number, we can just say we have 4 groups of the 2, which is really just 4 times 2, right? 4 times 2 is 8, 4 times 3 is 12, 16, and 20. And then this is what we would have on the graph. We just put those points on the graph there. And this one is not the same as the area, right? This one has a constant rate in the graph and the table. So we can see that this one would be linear. But at the same time, what is the dependent variable and the independent variable? We can see right here that the perimeter is depending on the length of the side, which must be independent then. So perimeter depends, therefore it's dependent on the independent, the side length. All right, write an equation to model P as a function of S. The perimeter equals the side length, and we have 4 of these, right? So we have 4 of these S's. This is one way to write it, the equation, but you may have also just said that we had 4 groups of S's. So either of these will work. Find an ordered pair that the graph passes through. Find another one. Well, we could just say we have a side length of 6, which would give us 24. But we could do something a little bit out of the ordinary and say, well, what if we had a side length of 52? Well, the perimeter would be 4 times that, and that would be 208. Not that it matters, you just get to choose, okay? And using the equation, it's just 4 times whatever the side length is, and that gives us the perimeter. What does the point 1040 represent in this context? Well, the 10 comes from the x's, which is this column here, the side length, and the 40 comes from the y, which is the second column, the perimeter. So in other words, if you have a side length of 10, your perimeter would be 40. Is this function linear? Yes, it is, because if we were to graph it, it would give us a straight line, right? If we were to connect these points. Straight line right there. And so that's the graph. Again, the table is going to show us a constant rate of change. So if I increase the side length by 1, the perimeter increases by 4. If I increase the side length by 1, the perimeter increases by 4. And it goes all the way down right here. And it's that constant rate of change that makes this linear. Now it could be scaled up, so if we skip 1 to 7, then of course we'd get 28, right? But if we look at the change here, that's plus 8, and that's plus 2. It still gives us the same rate, it's just been scaled up. And then finally the equation, which I guess we could say that the perimeter was 4 times the side length. Well, there's no exponents for s that we can see, and it gives us constant rate of change. In other words, it really is in this form, y equals mx plus b, which is a linear equation. Compare each of the graphs on the previous page to the graph of y equals x. Of course, that was the graph. Right, if we give ourselves some axes, the graph that just went through the origin, something like this. Well, if we look at all of them, it changes a little bit there. And there may have been a lot of different answers for this, but here's some stuff that you may be kind of interested in. The graphs intersect the axes, both go through the point 1, 1. However, yx goes through the point -1, -1, while x squared goes through the point -1, 1. And that's because we're squaring the x instead of saying that y is x. In fact, if we square it, we can never get negatives out of that square because a negative multiplied by itself will give us a positive value. All right, take a moment and answer these two questions. Describe the basic structure of an equation that defines a linear function. Think about the different forms of linear equation might take. Provide examples of the different forms. So take a moment and answer that question, and then once you're finished, answer number 9. Describe attributes you see in the equations that define nonlinear functions, and then provide examples too. Take a moment and do that, then we'll show you the answers here. And hopefully we see linear functions have either no variable or a variable with a phantom 1 for an exponent. So in other words, you can have y equals mx plus b, which does have a phantom 1 for its exponent. But sometimes we have straight lines, right? That was something like y equals 6. We've already seen that one. Nonlinear functions have a variable in the denominator or variables with exponents other than 1 or 0. And then in a very few special cases, we have the absolute value of x, right? If we look at y equals the absolute value of x, before that gave us a graph that looks like this, like a V. Well, it's straight until you get to this point, then it breaks off right there. So that was y equals x squared as well, or y equals 1 over x. All of these produced nonlinear functions because they were curvy on the graphs. All right, that's it. So take a moment here. You'll need to get the homework from the sub. If you finish this whole video, you should have finished the notes. And you should have everything on there. Of course, this video will be on YouTube so you guys can watch it anytime you need to, at home or, well, even if you're on vacation. So good luck with that. In any case, get the homework done. It is due by next time. We're going to take scores on both the homework that was due today, which was number 3, and then this is homework number 4 for Unit 5. We're going to correct that next time. All right, thanks for being good, you guys. Again, keep the noise levels down, and we will see you next time.